All right, so when looking at graphs and looking at the degrees, we're going to say a vertex in a graph is even if it has even degree. Likewise, we're going to refer to a vertex as odd if it has odd degree. And a graph is called k-regular if the degree is k for every vertex. Here, k is some integer. And oftentimes we'll use the word cubic to mean 3-regular. So that means that every vertex has degree 3 or is incident to 3 edges. And of course, this example doesn't meet that condition, but once I add in these edges, you see this is a cubic graph. So the theorem we're going to be interested in this video is known as the handshaking lemma. It's that the sum of the degrees of all the vertices in a given graph is equal to twice the number of edges. And a corollary of this result is that every graph has an even number of odd vertices. So here's the proof for the handshaking lemma. We want to show that the sum of the degrees of a graph is equal to twice the number of edges. And so we're going to do this using a method in combinatorics known as double counting. We're actually going to find some set x and show that its size is given by both formulas by counting the elements in that set in two different ways. So to that end, we're going to describe the set x to be the set of ordered pairs u comma e, where e is an edge and u is a vertex on the edge. In some contexts, we would refer to these as flags, because in other branches of geometry, you end up with this little picture like this when you go higher. But in this case, we're only working with 2 dimensions, so you just have the flag poles, I guess. So we're going to let x be the set of flags. Now, given any flag, we're going to delete the first coordinate. So in other words, given a pair of vertex and an edge the vertex is incident on, we're going to ignore the endpoint. So for any edge e, the pre-image of this edge has size 2 because every edge e has 2 endpoints. In other words, you're going to have a u comma e and a v comma e. And so that means that you can count up the number of flags by first, for every edge e, counting up the number of times it appears as a second coordinate. And as noted, that's always 2 times. So then we're adding up the number 2 over and over, and it's a fact that if you add up a constant over the elements of a set, you're going to get that constant times the size of the set. So you see that we have twice the number of edges as the number of flags. On the other hand, we could choose to delete the second coordinate. So given a flag ue, we'd find the function g by deleting the edge. Now, it follows that for any u, the size of the pre-image is the degree. In other words, given a vertex u, the number of ordered pairs we have is the degree because you have one ordered pair for every edge incident to u. So by the same logic as before, you could count up the number of flags by first looking at each vertex and counting up the number of ordered pairs where that vertex is the first coordinate. As already discussed, that number is the degree of the vertex. So we end up saying that the number of flags is the sum of the degrees. And thus we reach our conclusion. We have counted the number of flags 2 different ways. And so these 2 formulas must always give the same answer. As a corollary, we claim that every graph G has an even number of odd vertices. So based on the previous theorem, the sum of the degrees of a graph is equal to twice the number of edges. In particular, since there's a 2 on the right, we know that this summation must be even, which means if we work in modular arithmetic, the sum of the degrees has to be congruent to 0 mod 2. Now, meanwhile, for any individual vertex, the degree of that vertex is either even or odd. So either it's congruent to 0 mod 2 or it's congruent to 1 mod 2. And so if we apply this congruence fact to our summation, we see that for each odd degree vertex, when we're working mod 2, we get a contribution of 1. And for every even degree vertex, we get a contribution of 0. In particular, if we're working mod 2, the sum of the degrees is the same parity as the size of this set, the number of vertices of odd degree. Of course, we already know that this summation is also congruent to 0, so by transitivity, that means that the size of this set has to be congruent to 0 mod 2, Or, put another way, the number of vertices of odd degree has to be even.